Everyone, welcome to the data science seminar. It's a great pleasure to introduce Federica Arrigoni from Politecnico Milano. She's going to talk about viewing graph solvability and its relevance in 3D computer vision.
Hi, everyone, and thank you for the introduction. I will start this talk with giving you the outline of my presentation. I will start with an introduction that gives the motivation of this topic. Then I will introduce some background about cameras and multi-view geometry. Maybe most of you are already familiar with this. And then I will distinguish two cases, the calibrated and uncalibrated one, and I will explain the connections between these two cases and finally give the conclusion. So let us start with an introduction. This talk, and hence the topic of graph solvability, is strictly related to structure from motion. So what is structure from motion? It's an important problem in computer vision, and the goal is to recover two things. One is camera motion and the other is the scene structure, starting from multiple images, where camera motions refers to the poses of the cameras that took the picture, and the scene structure refers to a 3D representation of the points, usually in the form of a point cloud. We can represent this problem as a graph, which is called the viewing graph. And this will be the main character of this talk. In this graph, we have an image or a camera in each node. And then we also have connections between nodes. And it will be clear later what these connections are. For the moment, just think about some two-view relations. There are many approaches for structure from motions. We focus on a specific class of methods that are called the global methods. And these methods focus on only a portion of structure from motion, namely on the motion part. So points are not involved explicitly. In particular, we want to provide some theoretical analysis on this viewing graph. And this is the question that we will address during all the talk. So, for which graphs do we have a well-posed problem? And this should give the intuition that this is not obvious, as there are some graphs for which the problem is not well posed, and other graphs that are okay. And in particular, this is called solvable or not solvable. And more precisely, a well-posed problem means that we have a solvable graphs. And what is the meaning of solvable? The meaning is that the available two-view relationships, meaning the edges of our graph, determine the cameras in a unique manner. It will be clear later what we mean by unique, but just for an anticipation, we mean up to a single transformation. So, not considering this global ambiguity, solvable essentially means that we have a unique solution. So starting from our network of cameras, we can reconstruct uniquely the scene. And this is exactly what we would like in practice. However, there are also cases where we cannot do this. And in these cases, we say that the graph is non-solvable. And this represents the case where the problem has multiple solutions, and in general, they are infinitely many. Hence, this is the question that we will address during this talk. There are two aspects of the problem. One is solvability and the other is defective reconstruction. In this talk, we focus only on solvability, and there are many papers that address reconstruction, but this is not considered here. I just put a couple of examples in this table. And in particular, we will consider two separate cases. One is the calibrated and the other is the uncalibrated case. And I will explain the meaning of these terms later in the background. So why we need to check solvability? Actually, solvability means that the problem is well posed. So this is something that one should ask and check before running structure from motion. And this is needed because, of course, if a graph is solvable, then everything is perfectly fine. Our problem is well posed and we can address the reconstruction. However, if we are in a non-solvable case, we have a degenerate or ill-posed problem. And this means that it doesn't matter which structure from motion method we use, because the degeneracy is inherent to the problem, and so no method will return a useful solution. And this is why it is important to address this question before the reconstruction. Now, I have finished with the motivation, and I have prepared some slides about background related to cameras and to view geometry. I will go a bit fast, as I think some people already know this. And but this also helps to fix the notation that we will use and also recall the importance of the ambiguity present in the solution. So, how do we represent a camera? Geometrically, a camera has an optical center, an image plane, a coordinate system. And when we project 3D points onto the image plane, it's like drawing a line through the camera center and intersecting with this image plane. In formulas, we can represent a camera using a 3x4 matrix, which is named camera projection matrix. And in the calibrated case, it has this form. It can be decomposed as a calibration matrix, which is 3x3, a rotation matrix, and a translation vector that define the pose of the camera. And usually the calibration matrix contains some parameters that are specific to the camera, like the focal length, that identify the distance between the center and the image plane. And through this talk, we will distinguish between two cases, as already mentioned. The first is the case where the camera is calibrated, and this corresponds to the fact that this matrix is known. If we don't know these parameters, then we say that the camera is uncalibrated, and we represent it as a general matrix, 3x4, with rank 3. And everything here is defined up to scale. So in formulas, if we want to write the basic equation in multiview geometry, which is the projection of a point on the image plane, we can just write a matrix multiplication. And this is possible if we represent points using homogeneous coordinates. So 3D points will have 4 dimensions, and similarly image points will have 3 coordinates. And hence we can write that the projection of a point in an image is just the multiplication between the camera matrix and the 3D coordinates. So the previous equation was considering a single point and a single camera. but we can use exactly the same equation when we have multiple cameras. We just need to include some indices that refer to the proper point and the proper camera. So in this case, we have multiple cameras, multiple points, and the projection equation has exactly the same form. This helps to understand exactly what is structure from motion. So starting from the projection equation, structure from motion wants to recover both camera motion, which means the matrices of the cameras, and the 3D coordinates, which are both unknown. And we only know the projection of points in images. And this is a hard problem since we have many unknowns. Where this is the general uncalibrated case, where, as I already mentioned, in the calibrated case, we reduce to rotations and translations since the calibration matrix is known. Just some hints about the difference between calibrated and uncalibrated reconstruction. The uncalibrated case is the most general one, where we do not have any assumption about the model, and the reconstruction is projective, meaning that we may have deformations of this form. Instead, in the calibrated reconstruction, we have a metric reconstruction, of course, up to scale, but here we need to know in advance the calibration metrics, which typically involve the presence of some objects for calibration. Then, this is one of the most important basic concepts related to this talk, which is related to the ambiguities of the problem, hence the uniqueness of the reconstruction. Reconstruction is not unique at all, since it's defined up to a global projective transformation at scale. And this can be easily seen by multiplying points and matrices by one matrix and the inverse. Hence, we will not have only one solution, but the best things we can get is to have up to a single transformation. And this is what solvability does. We want to analyze the ambiguities inherent to the structure from motion problem, and in particular, when the solution is defined up to a single transformation, it means that the problem is well posed. Whereas when we have multiple ambiguities, so not one single matrix for all the cameras, then we will have a nil-post problems. Here we focus on a specific class of structure from motion methods that recover camera motion starting from two-view relationships. And in particular, these two-view relationships are the essential matrix in the calibrated case and the fundamental matrix in the uncalibrated case. That now I will briefly review. Basically, the fundamental matrix is a matrix that defines the relationship between corresponding points in two images. And this relationship is also called the epipolar constraint. And basically, it says that given a point in an image, the corresponding one should lie on a line. The important thing is that this fundamental matrix is something which is relatively easy to estimate, starting from point correspondences. In the calibrated case, this matrix is called the essential matrix, and it has an important property. That is, we can factorize this matrix and get the relative translation and the relative rotation between two cameras. However, we cannot determine the scale of the translation. Hence, we will only have the direction of the translation. So, just to recap, the important knowledge is that we have cameras represented as some matrices, and we can easily estimate this two-view relationship either in the form of some essential matrix or the fundamental matrix. And these will be the things that will be put in the edges of our viewing graph. Now we will focus on solvability in the calibrated case. So let us recall what is the viewing graph in this specific case. Is a graph where, as always, vertices corresponds to cameras or images, and in this case, edges represent essential matrices. And in practice, we don't have all the edges, but just a subset of them. And typically, this depends on the overlap between the field of views of the cameras. We want to establish if the graph is solvable, meaning that it determines a configuration of cameras up to a single transformation. And in particular, we will separate the reasoning between rotation and translation. And in order to derive these theoretical conditions on the graph, we will reason on what is the approach to solve for rotations and translation in a noiseless case. First, we start with this consistency constraint, which defines the relationship between relative pose and absolute poses of the cameras. We can conveniently represent the relative pose between two cameras as a matrix, and similarly with the absolute poses. And this constraint says that the relative pose is the product between the absolute pose of one camera and the inverse of the other. And this formula has a simple geometric interpretation, since it simply states that moving from one camera to the other is the same as moving from one camera to an external reference system, which is called the world reference system, and the first camera. So it's just a composition of transformation. Now we will look at this constraint in detail and split it into rotations and translation in order to separate the study of solvability for the two sub-problems. More specifically, we represent everything with these SE3 matrices that are 4x4 matrices that represent rotations followed by translations. Hence, each matrix will have a rotation block, a translation block, then zeros and one. These are unknown and represent the camera motion that we want to estimate, whereas the relative motion is known, since it can be derived from the essential matrix. Actually, as we will see later, it is not entirely known, since the translation is defined up to scale. But for now, we just look at these matrices and consider the consistency constraint and split it into rotation and translation. Hence, if we multiply these matrices, do some computations, and then look at what is the rotation, what is the translation block, we can split this constraint that links relative and absolute poses into rotation and translation. In particular, if we focus on rotations, we get a similar equation than the original one, where we have instead of the inverse, the transpose, which actually plays the role of the inverse in the rotation group. Hence, we have that a relative rotation is the product between the absolute rotation of one camera and the transpose of the other. And this is the starting point for reasoning about solvability for rotations. And this is the simplest case compared to translations and the uncalibrated case. Hence, we go back to our original question and ask specifically for rotations, in which cases we can uniquely recover camera rotations starting from relative ones. And always we need to take into account that uniqueness is always up to a single transformation, not uniqueness at all. And in order to answer this question, which is really an easy answer, we just rewrite the consistency constraint in an equivalent form, where we multiply both sides by this matrix. And this gives a constructive way to solve for rotations, since we can start with one rotation, we can arbitrarily fix to the identity, since everything is up to a global rotation, and then use this constraint to find the other one. This means that we fix one node in the graph, we use a tree of the graph, and we propagate the constraint along a spanning tree. And this will find all the rotations without, in an exact manner, if we assume a noiseless case. And this suggests that we can do the propagation through all the graph only if we have a connected graph. And this basically answers the question of solvability for rotations. Of course, this is not something really interesting because we always assume a connected graph. So this basically doesn't add anything to what is a standard assumption. And indeed, with a disconnected graph, it's like having different pictures of different cities around the world without any connection. Of course, we cannot get a unique reconstruction. The case of translation instead is a bit more interesting. And now we focus on this case. So we go back to the relation between relative and absolute poses that we saw in some slides ago. And in particular, we focus on the constraint for translation. If we do some sort of change of variables, which corresponds to working with camera centers instead of translation, then we have a very simple relation. Like the relative displacement between camera center is the difference between the speeds. And this is an easy relation, but we need to take in mind that relative displacement is not entirely known because we don't know the magnitude. Everything is up to scale and we only know the directions. Hence, in this case, the problem is to recover camera positions starting from pairwise directions. And once again, we ask when we can do this uniquely. And in this case, the uniqueness is up to a global translation and a global scale. Hence, our viewing graph here has these unknown locations of the cameras as nodes, and on the edges, we have the known directions. The important thing is that the relation between the directions and these unknown node locations can still be viewed as a linear equation, even if we do not know entirely the relative translations. And this now seems maybe irrelevant, but when we will move to the uncalibrated case, we will see that having a linear equation is something really important for practice. The case of translation can be addressed relatively in a direct manner because luckily this is not an unexplored problem, but it is a well-studied task. So it's not something specific to cameras and structure from motion, but is an example of a more general problem which is studied in other literatures like discrete geometry and robotics and control. And this is called bearing-based localization. And this is a good thing because we can use all the theory from this literature to answer our questions. And in particular, we have a characterization of which are the solvable graphs. And this characterization corresponds to graphs that are parallel rigid. So solvable cases are parallel rigid graphs. And what is the meaning of parallel rigid? The meaning is that a graph is rigid, like this example, when all the configurations with parallel edges differ by translation and scale. And here we have an example on the right of a graph that is not parallel rigid, also called flexible. And we can see this because we can alter this graph, as shown in the dashed lines, with some transformation that keep edges parallel, but this is not a translation and scale of the original solution. There are other transformations. And this is an example of flexible graph. And hence, this is the result for solvability for translations. Moreover, it can be proved that if cameras are on a generic configuration, so for example, they do not lie on a line or on a plane, then this concept of rigidity does not depend on the specific cameras, but is a property of the graph only. There are many different characterizations of parallel rigidity. The simplest one is a characterization in terms of linear algebra. So if we consider the equation that define the localization, we saw before that these are linear equations, then parallel rigidity is equivalent to check the rank of this matrix, where rank is not maximum since we have a translation and a global scale. And this is the simplest test for checking parallel rigidity. Hence, if the graph is parallel rigid, then we have a well-posed structure from motion problem. Otherwise, if we have a flexible graph, then we have an ill-posed problem. And in this case, since the problem is degenerate, the thing that one can do is to remove some parts of the graph and reduce the reconstruction to the largest rigid component, which is the largest subgraph that is solvable. And it can be proved that this can be done by analyzing the null space of the matrix that define the rigidity equations, and just do some clustering in the rows of this null space. There are also some necessary conditions for parallel rigidity. Actually, the importance of necessary conditions is that usually they are a simple way to detect non-rigid graphs. The first is a condition on the number of edges. So a rigid graph must have a minimum number of edges, otherwise it is not rigid. And moreover, a parallel rigid graph does not contain any bridge nor articulation point. And this means that it remains connected if we remove either one edge or a node. And here we have some example of articulation points or bridges, and this means that these graphs are not rigid, and hence they are not okay for structure from motion. We have other conditions for parallel rigidity. The first is a characterization of rigidity of a single cycle. In particular, we have that a cycle of length 3 and 4 or 4 is rigid, whereas longer cycles are flexible. And this condition can be used to derive some sufficient conditions for rigidity and hence build some larger graphs that are rigid based on the composition of short cycles. And in principle, one may argue that we do not need these sufficient conditions since we already have a practical characterization of rigidity based on a linear system of equations. But however, this condition helps to give some intuition on the problem and hence to get an intuition about which graphs are rigid or not based on the presence of short or long cycles, like the examples reported on this slide. I have also reported other examples taken from some real data sets that are typically used for structure from motion problems. Here we see a collection of data sets of popular monuments and some statistic about the data set, like the number of nodes, how sparse they are, and also the number of articulation points or bridges. And this analysis shows that most of the graphs are not rigid and only one of them is rigid. And hence, this suggests the importance of checking rigidity in practical structure from motion problems. And in order to give more intuition on these examples, here I reported some simplified representations of two datasets where the largest rigid component is drawn in gray, and I only reported explicitly edges outside the largest rigid component, just to see in a visual manner what happens on the non-rigid parts. So just to summarize the part about the calibrated case, we have seen that solvability for rotations is equivalent to having a connected viewing graph, whereas solvability for translation is equivalent to having a parallel rigid graph, which is something very understood in another community. Moreover, we have seen that we can test parallel rigidity in an easy manner just by checking the rank of a linear system. And also in a case of an unsolvable graph, we can extract maximal components just by analyzing the null space of this system. We also have an interpretation in terms of cycle, and we can process large scale datasets. So for example, the largest one that was processed here has 5,000 nodes. Hence, we can say that the calibrated case is a very good point. Now we move to the uncalibrated case, where we have uncalibrated cameras. So just to recall, in this case, our viewing graph has edges as fundamental matrices. And as before, vertices represent cameras. In this case, solvable means that the fundamental matrices uniquely determines the configuration of cameras up to a single projective transformation. And this is the question that we want to answer. Now we will follow a different approach than the calibrated case, and we will be a bit more formal, and we will directly reason in terms of the ambiguities in this transformation, rather than reasoning in terms of how reconstruction is performed. First, we will start with the definition of solvable graph, and of course, a similar definition can also be done in the calibrated case. First, we can define a notion of solvability that involves both a graph and a set of cameras. And we say that this pair, hence both graph and cameras, is solvable when all the camera configurations that have the same fundamental matrices as this camera configuration, they are all projectively equivalent, meaning that they are related by the same projective transformation. And this is the meaning of a solvable configuration of cameras in a combination with a graph. Specifically, it can be proved that this concept of solvability depends on the graph and the camera centers only, meaning that the other part of the 3x4 camera matrices does not explicitly influence the solvability, but just the camera centers. Then, if we consider a graph alone, we can say that the graph is solvable if it is solvable when we consider a generic configurations of cameras, meaning that the cameras are in a generic position and not on specific configurations like all on a line or on a plane. And this allows us to check solvability on a single example of cameras, provided that they are in a generic configuration, and this will imply that the result of solvability will be the same for all camera configurations on the same graph. The answer does not change because this property depends on the graph. And this allows us to speak about solvable graphs and non-solvable graphs. Also, in the uncalibrated case, we have some necessary conditions for solvability. The first is similar to the one for the calibrated case, which is a condition on the number of edges. So a solvable graph must have at least a minimum number of edges. In addition, as in a solvable graph, all the vertices have degree at least 2, and there are no 2 adjacent vertices with degree 2. And for example, thanks to this condition, we can say that these graphs are not solvable. In particular, we can observe that the square is an example of a graph that is solvable for calibrated cameras, but it's not okay for uncalibrated cameras. We also have some sufficient conditions for solvability. In particular, we have that calibrated graphs, triangulated graphs are solvable, so graphs made by triangles. And there exists also some constructive approaches in the literature that build solvable graphs in an iterative manner. We also have a characterization of solvability. However, I anticipate that this is not as simple as the calibrated case because we do not have a linear system, but we have a complicated polynomial system. And this is probably the most difficult slide of the two. So in this case, we will explicitly reason in terms of the ambiguities, namely which transformations we can apply to the cameras that do not alter the fundamental matrices. And in particular, we start by considering a single camera with center C, and we ask which are the transformations that can be applied to this camera that do not alter the camera, meaning that the camera matrix is a multiple of itself. And all the transformations that have this property has this special form, a multiple of the identity plus the camera center times any vector. And this result is the basic basis of this algebraic characterization. So this holds for a single camera, but in general, we have a graph with many cameras and many edges. And hence, we assign an unknown projective transformation to each edge in our graph. And we focus on 2 edges with a vertex in common. In this case, this transformation must act in a compatible way on the shared vertex. And this gives rise to the following compatibility condition. We have that the ratio between this unknown projective transformation has a similar form as before. Hence, some scale times identity plus the camera center of the vertex in common times any vector. And this is the basic equation for solvability. Just to recall, we have an unknown projective transformation for each edge. We have an unknown scale and an unknown vector for each pair of adjacent edges, whereas we consider camera centers as known since we work with generic configuration, and hence we can think about sampling at random a configuration of cameras given a graph and check solvability for this configuration. Given this characterization, we have that a solvable graph has the property that all these matrices are multiple of a single matrix. And what is the meaning? The meaning is that they are up to scale the same projective transformation, and this is exactly the definition of solvability. And in addition, it can be proved that this is equivalent that these vectors vanish for all the edges. So just to recap, we have a polynomial system of equations with many unknowns. And this was derived in a previous paper, and it was posed just as some theoretical characterization without a practical algorithm, since it is very demanding to solve this system of equations. In a recent paper, we show how to eliminate some variable and hence reducing the complexity of the problem. I will just give some hints about this procedure. The first step is to focus on a different representation of the problem, where we work on another graph, which is called the line graph. This is a notion in graph theory. It was not invented by us, and it's a graph where each node is an edge of the original graph. And we have an edge if the corresponding edges in the input graph have a common vertex. And this helps us to count the number of equations in this complicated polynomial system. In particular, we have that there is one equation for each edge in this line graph. And in addition, we give a name to the right term in this basic equation, and this will call Z matrices. And this helps to simplify our system. The intuition for the simplification is that we want to remove these G variables. And the idea is just to multiply the Z matrices along the cycles. And this has the property that some common terms vanish, and this gives the identity. And this is the basis of this reduced formulation. It can be proved that the equations that define solvability are equivalent to the cycle consistency equation, where the product of Z matrices along cycle gives the identity. And these involve only the scale and the vector as unknown, not the G matrices. Hence, we have a reduced set of equations. In particular, it can be proved that we do not need to consider consistency on all the possible cycles of a graph, but just on a specific basis, which reduces the complexity of the problem. We can consider a further simplification. Instead of considering both scales and vectors as unknown, we can divide each vector by the scale and have one single variable. And this can be seen as a minor trick, but it's really important because it implies that in a solvable graph, we have exactly one solution. And hence, we remove all the ambiguities. Just to recap the algorithm, we have as input a graph. We want to say if it is solvable or not. We start by sampling at random a configuration of cameras. And this can be done since solvability depends on the graph only if the configuration is generic. We then compute the line graph as explained before. We extract a basis for this graph. In particular, the simplest one can be derived from a spanning tree by adding non-tree edges. Then we set up equations. As seen before, we also need some auxiliary equation to enforce that our matrices are invertible and scales are non-null, and then we compute the number of solutions. And this is the most complicated part of the problem because it requires Grosvenor basis computation, which is extremely demanding. Here are some examples of graph with 9 vertices. The first line are solvable graphs. The second line are non-solvable graphs. And here one can see that we probably miss some interpretation about what is solvable and non-solvable because there is not a clear difference between the structure of non-solvable cases and the one of solvable ones. As already mentioned, solving polynomial system is really demanding. For example, it took more than 4 hours to check solvability on a minimal graph with 90 nodes. And this was the largest example that we were able to process. These are examples of solvable graphs, in particular minimal graphs, meaning that they are graphs with the minimum number of edges that are required to be solvable. However, if we consider graphs that are more dense, hence with more edges, then complexity becomes even higher. In particular, we were not able to process some standard real data set in contrast to what was done with the calibrated case, but for real viewing graphs, we were only able to analyze solvability on some subgraphs which were sampled from this real data set. And we saw that there are some cases which are solvable, other cases which are unsolvable, and some were detected by our approach or either by some sufficient or necessary conditions. To summarize the uncalibrated case, we show that we can reduce the number of unknowns thanks to cycle consistency. And this in particular help us to classify many cases of graphs that were not classified by previous works and process graphs with minimum number of edges up to 90 nodes. However, we were not able to process larger or denser graphs. Before going to the general the conclusion, I will give some hints between the connection between the calibrated and the uncalibrated case. It can be proved that a graph that is solvable in the uncalibrated case is also solvable in the calibrated case, and hence is parallel rigid. And surely this is not something surprising, but it's a very expected result, because a problem that is well posed with uncalibrated cameras that are more general than calibrated one is also well posed with calibrated cameras. And this can be proved by using some characterization of parallel rigidity and a necessary condition for solvability that have a similar form and involve accounting on the partition of the edges of a graph. Now I give a general conclusion to this talk. So I spoke about solvability both for the calibrated and uncalibrated case. And we saw that the formulation of solvability for a calibrated case is really simple, a linear system. And we can handle large-scale data sets. We also have an interpretation in terms of cycles in the graph. And finally, in a non-rigid graph, we can extract the components by just computing the null space of a matrix. And hence, we can, in some sense, consider the calibrated case as a solved problem. However, we cannot say the same for the uncalibrated case. This is a much harder problem. The hardness derives from the fact that we do not have a formulation in terms of a linear system, but we have a much complicated polynomial system. And due to this reason, at the moment, only small-scale graphs can be processed. Moreover, as seen in some example, we don't have a clear interpretation of what is solvable and what is not in terms of the structure of the graph. And finally, the task of computing components have never been addressed so far. So there are many open issues for uncalibrated solvability. I conclude with a list of references related to this work. And finally, I thank you for your attention.
Thank you, Federica. It was very interesting and very well organized and right on time. I appreciate all the background because we have, audience with different background. Yeah, so it was very clear. I'm trying to think. One thing that I was not sure about, and it's something very basic, but how did you choose the basis for the cycle consistency?
Okay. Actually, I was quite fast in some part because this is some dense topic, so it's not possible to give all the details. We can consider a tree of the graph. And for example, in this graph, the tree is with the non-dashed arrows. Then if we have a tree, every edge, if we add an edge not in the tree, it generates a cycle. And this is called the fundamental cycle basis. Is a basis generated from a spanning tree just by adding non-tree edges.
Yeah, thank you.
I actually had a question. Hi.
Hi.
Federica. So very nice talk. Thanks for going over this in detail. I was curious what happens if there's like noise in the graph structure, like if you add like an edge that's not supposed to be there or something. I guess this would mean that the algorithm would always return it's not solvable, essentially.
Yeah, because this concept depends on the graph. So
yeah,
if it's not solvable, the answer is not solvable. And this actually happens in some data sets. For example, here we have many pending edges, meaning that there are, let's say, one image that is connected to only one other image and nothing more, and this cannot be solved.
Okay. Yeah, have you thought about if there's a way to be able to handle some corrupted edges in the graph, or maybe this is very hard with what you're doing?
To handle what?
Like to be able to handle a graph that has like say the graph is solvable, but then I add like k edges at random, corrupted or something. Is there a way that you could figure out which edges were corrupted?
I mean, if it's already solvable and we add edges, it remains solvable. We just add the redundancy. On the contrary, if it's not solvable and we add edges, we don't know if we are adding the correct edges. We can just check the new problem if it is okay and know later. But for sure, we can also reason in terms of how to build surely solvable graphs. And this is what is done mainly by constructive approaches, which typically start from triangles and so on.
Right, but so I guess I'm thinking that when you add an edge, there's an object attached to it, right? Like the transformation between the two viewpoints. Right?
But if we add edges, we are not adding nodes.
Yeah.
Basically, I didn't say this, but I mean, a solvable graph is equivalent to a complete graph because it's well posed and it's the same as having all the edges, all the fundamental matrices. It's like if we have a unique configurations of cameras, we can implicitly compute the remaining ones. So adding edges is not a problem as soon as we are not adding nodes. I mean, adding edges on nodes that are already there. If we are adding new nodes, then it's different.
Okay, thanks.
You can still, so suppose you add nodes, but you can still have some ideas about removing some of the, corrupted edges or.
I mean, you can do in simple cases like here. If there are these pending edges, then you are sure that it's not okay. You can easily detect and remove.
I mean, so sort of what I'm thinking is like in practice, you get these edges by matching up different viewpoints.
Yeah.
Like you match up key features in the images or something, and you try to match this up. But this must fail sometimes, right? You must have cases where you think that they're matched up, but they're actually not, or you get the wrong transformation between them or something.
You mean this by corrupted edges. So you have the edge, but the transformation is bad.
That could be one case, is like, yeah, like there's an edge in your graph, but you have the wrong transformation across it or something.
Okay, actually this is not managed because this concept of solvability is related to the graph. So you don't care about the actual fundamental matrices or matches that you have. You just ask this. I have this structure of connection. Is this structure enough for a unique reconstruction or not? You don't consider the specific values. Actually, the solvability with noise has not been studied.
Okay. Okay, thanks. Yeah.
Yeah, thank you. I see, let me share it with everyone. There is a question. Thank you very much for the great talk. Do you see any generalization to hypergraphs for trifocal tensors or quadrifocal tensors, or do you think it would just be better to extract fundamental metrics from those objects to form the current graph?
Actually, at the moment, there is no extension, but my feeling is that it may be limited because trifocal tensor is like having a triplet of cameras, so a triangle, but this solvability consider even cases where we don't have only triplets. So focusing on triplets only may be not capturing all the possible situations, but for sure it's interesting to reason about other representations. Maybe it can help.
Okay, thank you. Yeah, thank you very much. So if there are no more questions.
Thank you.
Yeah, let's thank the speaker again. Okay. Yeah, so Georgia, you can stop recording.
Thank you.
Yeah, if it's not no recording, right? Georgia.